Okay, we now move to the importance of Newton's law of universal gravitation. We started this journey into space a few months ago, and we firstly had a look at Newton's law. And as we've gone through, we discovered that Newton's law has been central to our understanding of most of our how to get things into space. All the way from over here, the energy, the gravitational potential energy. The second one over here is the escape velocity, orbital velocity, and Keplers Law. All have been derived from a central understanding of Newton's law of gravitation. So how did we derive these, and how was using this law at the centre here important in getting all the other understandings that we have come along the way for motion of satellites? Well, the first thing we looked at was the gravitational potential energy. So when looking at this one here, we know that the gravitational potential energy is defined as the work needed to move an object from the surface of a planet to an infinite distance away. And the distance that it moves away will take from the centre of the planet, so I can't go all the way there, out, and we're going to call that R. So our R distance can be anywhere along the way here, and that is from the centre of this planet. When we are an infinite distance away, then we have no tendency to fall back. There's absolutely no gravitational pull from the planet back, so we set this level out here as 0 EP. So this is where EP is 0. We also then maximise EP as on this surface of the planet. This means that all of the values of EP between the surface of the planet and the infinite distance away would have to be negative for it to grow to 0 from being the maximum value in the negative direction. And we know that it has a shape like that. So that's a quick summary of the way that we looked at EP to begin with. But how did we get to getting the formula for EP? Well, we defined the gravitational potential energy as the work needed to move it to an infinite distance away. And work, as we know, is equal to Fx. It's a force moving something through a distance. That is the work, that's the definition of how work is done. So the force in this case is Newton's universal law of gravity. So it's a gravitational force, so it's capital M, little m on r squared. And we're using the convention all the way through this that capital M is the object's mass, the mass of the central object, in other words, the mass of the planet or the mass of the centre part of the orbit, and little m as being the mass of the object which is in motion or moving, referenced to that planet. It just makes the laws, the equations, so much easier to work with without using the subscripts. So that's the force. Now we have to multiply by the distance that it travels through, and the distance that it travels through is from the centre of the massive planet, and it is r. So when we cancel these r's, we get that work is equal to gmm on r. But by definition, as the way we just reasoned there, it must be negative. So EP becomes the negative version of negative mm on r. So that was the first understanding that came from Newton's law of universal gravitation. We then moved on, because we now have this understanding that EP is equal to minus gmm on r, that this is the energy needed to move it from the surface of the planet to an infinite distance away. And the way that this work is required, this work, it's W, is given, can be given in the form of kinetic energy. So if we say that the change of kinetic energy, the change of potential energy is equal to the kinetic energy given to an object, say, which we launch it through on a launch pad, or we project it into space like a cannonball. If we project the value, the object, we give it kinetic energy, and if this kinetic energy matches the work, it will move it to an infinite distance away. So this is the kinetic energy needed to move it to an infinite distance away, and this is the change in potential energy. We know that by definition, EP at an infinite distance away is 0. So EP would be, final condition is 0 minus the initial condition, which is negative GMM on R, and therefore EP, delta EP, the change in it becomes equal to GMM on R. So we know that side of the equation. Secondly, we know that kinetic energy is given as a half mv squared. So using this understanding that the change in potential energy must be given by kinetic energy if we want to move it to an infinite distance away, then by equating both sides we get GMM on R equaling a half mv squared. Remembering we kept the convention that capital M was the mass of the centre of the orbit or the central body, and M is the movable body that moves away or is in orbit around it. So in both cases here, these M's are the same, and that equates to, if we arrange that, that V squared would equal 2gm on R, or leaving us that the escape velocity is equal to square root of 2gm on R. Why is this escape velocity? Because it would move it, that's the energy required. This is the kinetic energy which is required to move it to an infinite distance away. And at an infinite distance away, it will have no tendency to fall back to the planet or return. So therefore, this would be the amount of energy needed to remove the planet for it to never return. And a velocity such as that is given by 2gm on R. So that was our second thing that came from that. So we've just discovered that these two thought bubbles are very closely linked. We now move on to the orbital velocity, and the orbital velocity was derived in a different way. It's not working with energies but with forces. And with this one here, we said that the centripetal force and the gravitational force became the same. And the reason why we can say this is that we understand that centripetal force is a force that creates a motion in a circle. So it gives a circular motion. And by itself, it doesn't actually exist as a force. It is created by other forces. So when we were discussing atoms going around the nucleus, electrons going around the nucleus, the reason why they went around as in, we'll say, in circular orbits was an electrostatic force. So the electrostatic force was the equivalent to the centripetal force. Now, for a planetary motion or an orbitary motion, we know that if we have a central body of mass m, capital M, and an object going around of little m, then the force between them is the force of gravity. But the force of gravity up here causes this motion in a circle, therefore the force of gravity must equal the centripetal force. The force of gravity, as we know, is given by universal law, which is Gmn on R squared, and the centripetal force is mv squared on R. Once again, because we've used a convention of little m's and capital M's and R being the same in all of these formulas, R being the distance away from the central objects, so the capital M centre, then we can do a lot of cancelling in this case. So we can cancel the m's here, we can cancel one value of the R, and we get v squared equals gm on r, or v equals gm on r in the square root. And so this gives us our understanding of the minimum value for velocity to be for an orbit to occur. And we know that this would give us a circular orbit. So at this exact orbital velocity, we would have a circular orbit. And as we increase between the orbital velocity and the escape velocity, the difference between them is a factor of root 2, which is 1.41. As we increase our orbital velocity by a factor of 1.41, towards that, I should say, we get a more of a elliptical orbit until eventually at root 2 times the orbital velocity, we will achieve escape velocity. So we are left with Kepler's law. So once again, to recap, EP is work times, work, which is force times distance, and then this led us with potential energy equaling kinetic energy. Here we equated gravitational force and centripetal force. These two original ones are linked, and so are these two linked together. We now know that the requirement for a circular orbit is v equals the square root of gm on r. If we also think about it, because we are in a circular orbit, and we know that a circular orbit of a specific radius has a circumference of 2 pi r, and if this takes place in a time period we can call capital T, then the velocity would equal 2 pi r on capital T. So these two velocities here, that velocity there and that velocity there, must be the same. So by equating, we get the square root of gm on r equals 2 pi r on t. By simple rearranging there, by squaring both sides, we get our final result, which is, that becomes gm on r would equal 4 pi squared r squared on t squared, and then rearranging that into our normal form, we want r cubed on t squared equaling gm on 4 pi squared, which is Kepler's law. So far we have 4 pieces of information that have come simply from our understanding of Newton's law of universal gravitation. The last thing that we want to have a look at is the orbital energy. Now, the orbital energy, as we know, all objects would be the sum of all the energies that they have. So if I have E, orbital, just mechanical energy we'll call it, then if I'm a satellite in an orbit, or I'm a satellite moving around in space, then I would have potential energy plus kinetic energy. And my total energy, which is called E total, would be the sum of those two. So we know that this would be minus gm m on r, and our kinetic energy would be a half mv squared. Now, if I'm in an orbit, then my v would equal gm on r when square rooted. And that means my v squared would equal gm on r. Placing this value into the formula over here, we get minus gm m on r plus a half m and gm on r. If we think about this, this equals minus gmm on r plus gmm on 2r. And that simply is this number here is double that number there. And just by subtracting, you get minus gm m on 2r. Okay. Because this one here is half that value being negative. So the total energy that a satellite has at any point here is equal to minus g m on r. And from our last discussion, we know that we use a figure called the epsilon, which is the specific energy. The specific energy is the total energy per kilogram of the orbiting satellite. So it just removes that m. So it's minus g m on r. And it is, in fact, if you have a look at it, it really is just the square of the negative square of the velocity, the orbital velocity. But we now know that our total energy in an orbit is given by that, and then we can look at orbital decay coming from this. What would happen if my satellite slowed because it lost energy with friction to the friction with the atmosphere? So if E was to reduce, then R must also reduce because it's a negative value. And so we can understand orbital decay. So there are 5 things here that all rely on Newton's fundamental law that he determined about gravitation. So in summary, Newton's law of universal gravitation gives us methods by which we can calculate the motions of satellites. And in 5 ways we can do the course. By measuring its gravitational potential energy of the satellite, its escape velocity and orbital velocity, its period and its radius, that's by Keplers Law, and also finally by orbital energy. And don't forget, when you're mentioning all of this, that we can also work out the gravitational force on the satellite, which is given by that formula, because little m in this case here is the mass of the satellite. So there are 6 things all up, and as a result you can quite give a very detailed response to such a question in a HSC about all of the emotions that are able to be derived from a single understanding of one law of universal gravitation. Thanks very much.